Now we're recording, so if you want to make fun of me, it'll be recorded for all posterity. All right. Now, if the pen works, then we'll be in business. Oh, it does. Excellent. Good. It works. That was exciting. So, if you ever want to go back and listen to this particular lecture, it'll be on YouTube. So, on my channel.
It's pretty dry since Diffie Q.
It has been pretty dry since Diffie Q, but I had, with the last time I taught this class, I recorded all the lectures, and people can go back and watch. I mean, if it helps, I'm more than happy to do that. It's just, of course, I have to write everything on the screen that way. Which, since these other TVs don't work, it's harder for people to see in the back, and that was why I've been doing it on the board. But willing to do whatever.
Do you have last year's lectures recorded though? Is it on
I don't know if they might be on there. But Diffie Q is definitely still on there. I haven't deleted anything off YouTube, so. But you can find my YouTube channel. Monica subscribes to my YouTube channel. There's not been anything on there since Diffie Q, but. Alright, anyway. Any questions at all about anything before we get going? Yeah, Sydney.
Is there a time limit for the test or just however?
Whatever. Yeah, that's how I usually am about it. It's like, yeah, whatever. Yeah, Kelly. Yes, I assigned homework last time, right?
She wasn't here.
Oh. So I have it handy. I'm not even sure I have it with me. Oh, maybe I do. Oops. That look familiar? I wasn't sure the battery would be working in this pen. It was my main concern with this whole process. So far, so good? All right. Did you get it down, Kelly? Okay. It's so huge at the top. Do that. There we go. It's a little better. All right. So we've talked about confidence intervals for means. We've talked about confidence intervals for difference of means, for paired differences of means, for variances, and for ratios of variances, right? So last one we need to talk about, this is section 6.5, is confidence intervals for population proportions. So what we really mean by this is that you're running a binomial experiment over and over and over and over and over and over again, and you're counting the number of successes of that particular binomial experiment, and you would like to know what the true proportion, what the true probability of success is, what numbers those lie in between, right? So much like we do for, okay, if we're going to run random samples over and over and over and over again, where does the true mean lie? Same idea for confidence intervals for those means. We're doing the same thing here for proportions. So much like what we've talked about before, if we run if we have our sample sizes large enough for a proportion, we know that the distribution is going to be, it can be approximated by a normal distribution, right? So we've talked about this before. If n is large enough, we can approximate the binomial with the normal distribution, what were the mean and the variance for the normal distribution that we can approximate the binomial with? Okay. Okay. So we can calculate the mean, we can calculate the variance in this particular fashion. Now again, if we're thinking about doing this over and over and over and over and over and over and over again, we're going to want to talk about doing central limit theorem idea to get that approximate normal distribution. So if we think about this, if we think of y counting the number of successes, we can standardize this thing by doing y minus the mean, right? And then square root of the variance on bottom. We know that this is standardizing things, right? And then if we want to rewrite this as actual proportions, if p is the parameter we're trying to get at, I can divide top and bottom by n to get to y over n minus p. And then if I divide bottom by n and bring in the n under the root, we'll get square root of p times 1 minus p over n on bottom. So this is approximately normal 0, 1, if n's big enough. This should all sound familiar, right? This is central limit theorem idea. And all I did was a little bit of algebra at this point. All right, so again, the whole point of this is to try to get a confidence interval for p. That's the thing we're trying to approximate. So it's approximately normal 0, 1. One of the ways we can approach this is to do the same tack that we did with doing confidence interval for mean, right? We can set this up for the probability that this is in between two values, call them z sub alpha over 2, and a negative z sub alpha over 2 and z sub alpha over 2. Is 1 minus alpha. This is how we attacked the mean, wasn't it? We had x bar minus mu over sigma over the square root of n. Notice that this part here really does look like the variance over the square root of n part again, the standard deviation over the square root of n, right? Or variance over n. Yep. Okay. So, yeah. Hmm?
Is the over n in the square root?
It's under the square root, yep.
Okay.
Yep. Not a dumb question. That's important. It's under the square root. That's not a dumb question. It's in the square root. Thank you for asking that, though. All right. So then we rearrange things, and again, this p is what we're trying to get a handle on. So we can multiply through by the standard deviation, and then move around our y over n pieces, right? So we'll get to probability that y over n, oops, let's write it this way, sorry. Y over n minus z sub alpha over 2 square root of p times 1 minus p over n is less than or equal to p is less than or equal to y over n plus z sub alpha over 2 square root of p times 1 minus p over n. That probability needs to be equal to 1 minus alpha. But again, just to emphasize what's going on with the form of this thing, here's the parameter we're trying to estimate with an interval, the p, right? The y over n would be your point estimate. It's number of successes over that many trials. So this would be your point estimate here, much like it was for the mean, right? When we did the confidence interval of the mean, we just had x bar there. Okay? Z sub alpha over 2 is in the same spot. Okay? This part here is just an approximation for the standard deviation of our population over the square root of n. Right? Same idea. Same stuff that we did before. Now, we could do this in a different fashion and actually end up with a different confidence interval, which we'll see here in a minute. But the important part here is that, of course, we run into the same kinds of things that we did with means. We don't typically know what the population variances for means is, so we have to do approximations to those things, right? Now, if the sample size is large enough, we used the unbiased sample variance and said it was approximately normal. If the sample size wasn't large enough, we still used the unbiased sample variance, but we used the t distribution instead, right? But in both cases, we didn't know what the population variance was, so we had to use an estimate for it. So it's the same idea here. I don't know what the population variance is in general. In particular, it's because it depends on the parameter that I'm trying to estimate. So there's a couple of ways that you can handle it. Either you can use the population proportion that you get and use it for a point estimate. Not a bad idea if n is large. Okay? If n is large, we should have a pretty decent point estimate for it. The other thing we could use, just to make sure that we are making our interval big enough, the other thing we could use is think about what the absolute biggest this could possibly be, no matter what the p is. P times 1 minus, if you just think about it as a function, this is an algebra object, a function. What kind of function is p times 1 minus p, or x times 1 minus x? What kind of function is that? Yeah, it's quadratic. It's an upside down parabola, right? Where does it cross the x-axis if I think of it as x times 1 minus x? At 1 and at 0, which means its high point has to happen at... Yeah, where between 0 and 1 since it's a parabola?
Oh, well, different.
Yeah, it has to be a half, right? Parabolas are symmetric about their axis of symmetry, which would have to be halfway in between those two roots, right? So the bit in particular, my whole point of that little discussion is the biggest this can possibly get in the numerator is a half times a half. So the biggest the numerator this could ever get is a quarter. So if you wanted to make sure that you've got this thing as big as possible, use a quarter on top. Not as important if you already have a point estimate. What's important with this is if you're looking for margin of error type things, and I want to know how big your sample size needs to be. Because in those cases, you don't have an estimate yet for what the population parameter is. Right? You don't have an estimate for that population proportion. I said parameter the first time. You don't have an estimation for that proportion. So the safest thing to do would be to make that numerator 0.25 and then calculate what sample size you would need. Does that make sense? Because no matter what the population is, the biggest this numerator could possibly get is 0.25. So your safest bet to make sure that you've got your n big enough to get this tolerance small enough is to use 0.25 up here and then solve for your n. We haven't done too much with sample size computation yet, but you can imagine to say, I want this tolerance here to be, say, within 3 percentage points. You see that a lot in polls, right? You'll see a poll for election results or approval ratings or those kinds of things, and you'll see the margin of error is plus or minus 3 percentage points. The way they can get those margins of error is to make sure that they've sampled enough people to get their opinion, yes or no, Democrat or Republican, what have you. They've sampled enough people to make sure that this number here isn't too big. It's within 3%. That's the idea. It's not a hard, you can imagine how to solve that equation. It's not a hard thing to solve for, right? Because you would put, if you wanted this to be 0.05, you would put 1.96 here for your z sub alpha over 2, right? And then just set that equal to whatever the margin of error is that you want to solve for n. Then you can do the same thing with means and anything else. You're just trying to figure out what the n needs to be. And notice in all of the formulas, your n's are in the denominator. So if you want the margin of error to be less than something, when you move the n out of the denominator, it's going to make the n bigger than or equal to something. It's not, like I said, it's not a difficult thing to solve for. All right. Anyway, this is how you can set, this is one way that you can set up your confidence interval. And again, if your n's big enough and you've got your p calculated, using that actual p in here, not a big deal to do that for the standard deviation approximation. If you want to make sure you make it as big as possible, use 0.25 instead. All right. This was not the only way that we could have attacked this problem to make a confidence interval. Now, we're going to do this in a slightly different way and show that we actually come up with a different confidence interval. We could have done the same plan of attack, by the way, for means, but we didn't because you end up with the same confidence interval. I'm going to email you a file that shows that if you, the second approach that we're going to take to confidence intervals, if you do it with means, you end up with the exact same thing. Okay, which is why we didn't do this for means at all. You just end up with the same confidence interval. But what we do for population proportions, we're actually going to end up with a different interval. So, to that end, instead of going from this line to this one, let's instead go this way. We want the probability that the absolute value of y over n minus p over square root of p times 1 minus p divided by n is less than z sub alpha over 2. Let's say that equals 1 minus alpha. Well, basically, now I'm just trying to solve this inequality here, right? Instead of rearranging it and putting the p in the middle, I could think of trying to solve this inequality. The way it's written is kind of ugly to try to solve it, so what I'll do instead is square both sides, because that'll make it better. I'll make the absolute value go away, right? So let's just worry about solving this inequality. Let's square both sides so it gets rid of the absolute value. It also gets rid of the square root in the denominator. All right, so let's just rearrange some things here. Let's clear the denominator first, and as I clear the denominator, I'm going to FOIL out the numerator. So I'll have p squared minus 2py over n plus y squared over n squared. Right? Is less than or equal to z sub alpha over 2 squared times, and I'm just going to distribute the p through, so I'll have p minus p squared all over n. Okay, I know this doesn't look exceptionally pretty. I agree with you, okay? However, this is quadratic in p, right? So if I move everything over to the other side, I should be able to check when that thing is less than or equal to 0 by figuring out where its roots are. It'll be less than or equal to 0 in between the two roots. In particular, I know it'll be less than or equal to 0 in between the two roots because I'll have a positive coefficient on the p squared term, which means it had to be a parabola that opens up. So it has to dip below the x-axis in between the two roots, right? We agree with that? Okay. So if we move everything over to the left-hand side and collect like terms, notice that your coefficient on the p squared will be 1 plus z sub alpha 2 over z sub alpha over 2 squared over n, right? So we'll have 1 plus z sub alpha over 2 squared over n times p squared. All right, let's look at the coefficient on the p term. Both of them will be minus, right, when I subtract it over. And I have a 2y over n, and then we'll have a plus a z sub alpha over 2 squared over n. Both terms on the right-hand side had a p in them, the p that we're trying to solve for. So there wasn't a constant term in particular. So I just have now plus y squared over n squared. I want that less than or equal to 0. Oops, forgot my p here. Sorry. That was the coefficient. That was the coefficient. This part right here was the coefficient on p. I forgot to write the p in there.
So for y, we're just using the random variable?
Yep.
Value?
Yep. Y is counting the number of successes.
1?
Y is, it's counting, because we're doing a binomial random variable. So the y is number of successes here.
Right, yeah.
Okay. Oops. In fact, the y over n would be giving us our maximum likelihood estimate for our p.
Yeah. Yeah.
Yep. All right, so if we use the quadratic formula, the zeros would be negative b. So this is our b here, right? Negative b would just change that to a positive sign. So we would have 2y over n plus c sub alpha over 2 squared over n. Right? That's the opposite of b. And we'd have plus or minus square root of, oh, that's messy, 2y over n plus z sub alpha over 2 squared over n squared minus 4 times a times c, which is just the y squared over n squared, all over 2a. Yeah, well, it would have been a lot better to do that originally. I could expand it to the whole screen. Why didn't I just do that to start with? 30 minutes into class, I finally figured out how to use the computer. Told you it's been a while since I used this to teach with. All right. Wow, that doesn't look much nicer, does it? Let's see if we can make it look a little bit better. All right. Now I'm going to take this 2 that's here, and I am going to divide it through everything. Okay. So here we would get y over n plus z sub alpha over 2 squared over n. All right. And then this is over 1 plus z sub alpha over 2 squared over n. Now, why did I write it like that to start with? This is definitely different than what the original confidence interval we came up with looked like, right? This is now what we're using for what would be our point estimate or our center of our confidence interval, right? Because that's the part that's in front of the plus or minus. I'm going to do the rest of it here in a second, okay? But this is the part that's in front of the plus or minus, rather than what we had before, where the part in front of the plus or minus would have been just the y over n piece, right? Because here's the plus, here's the minus, okay? So instead of using the y over n as the point estimate, it's using this thing as the point estimate. Okay? Yes? Oh, yeah, we would. Thanks. Sorry, there's a 2 here. Yeah, thank you. In the second one, but not the first one, because there was a 2 in front of it. Thank you, you're right. Yep, there should be a 2. Still, same idea. This is point estimate, right? For what we have? Okay. Now, what happens to this point estimate as n gets bigger and bigger and bigger and bigger? Well, as n gets bigger and bigger and bigger and bigger, what happened to these two terms? Yeah, they get closer and closer to 0, and what do we end up with? Y over n, right? So as n gets really, really large, this is essentially the same point estimate that we had before, right? So there's not going to be much benefit to using this confidence interval for large n's, because it might as well be the other one. In terms of the point estimate, let's see if the same thing happens for the standard deviation estimate as well, margin of error estimate part. All right, so to that same end here, going back up here, if we pull in, I want to divide top and bottom by 2. When we pull in a 2 into the square root, it becomes a 4, right? Okay? So when we pull the 2 into the square root, it'll become a 4. It'll kill this 4. This is going to be a 4 when we square it out as well, won't it? So we'll have, let's see if we can figure this out. This will still be all over 1 plus z sub alpha over 2 squared over n. Square root of, all right, when we FOIL this out, this part becomes 4y squared over n squared, right? But we'll divide it by 4. So we're just going to have y squared over n squared. Do you agree? Because we're pulling this 2 inside the root. Okay. Also, when we FOIL it, we're going to get a 4 as our coefficient, aren't we? In front of the mixed term. So again, that'll cancel out. So we're going to get plus y, I'm going to write it as y over n times z sub alpha over 2 squared over n, just for time being. And then a plus, I'm going to get a z sub alpha over 2 yeah, it's still squared, so it's going to be to the 4th over n squared. And then on the end here, the 4's will cancel, so we're going to get a plus a y squared over n squared plus another y squared over n squared times z sub alpha over 2 squared over n. All right, let's see if we can play around with that a little bit. Try to get this to work out the way I want it to here. So yeah, one too many terms in there. Oh, they are negative. Thank you.
Second last.
Yeah, this one is, and this one is. Thanks. That's my problem. That's why things weren't canceling. Thank you. All right. So now some things happen, right? That actually helped. Thank you. That minus sign to go away. This one and this one go away, right? That was the piece I was having trouble reconciling, was literally that piece. All right. If we look at this one here, this term here that I'm underlining, and this term here, they share a common factor of z sub alpha over 2 squared and a y over n, right? So those two together have a z sub alpha over 2 squared times a y over n. And we're left with, in the first one, we're left with a 1. And the other one, we're left with a minus y over n. No, I'm left with another, I forgot to factor out my over n here. There's an n here too. Because it's z sub alpha over 2 squared over n. I forgot to pull that whole n out. Okay. Sounds good. Good. And then I've got a plus z sub alpha over 2 to the 4th over n squared.
4n squared?
Oh, yeah. There's a 4 in the crud. There's a 4 here, isn't there? Yep. I divided out the 4 in the first two terms and forgot to put it in the last one. All right. Whew, what a mess. Okay. We're getting there, though. I promise. All right, let's look at this piece right here that I'm circling. What does that look like, the piece that I just circled? Okay, so yeah, it looks like the p times 1 minus p all over n, right? Which was here, right? In the original? Well, I guess technically here, wasn't it? That looks like the p times 1 minus p over n, doesn't it? Now notice, I'm not going to rewrite this whole thing over the bottom again because I'm just interested in this top. Notice I've got a z sub alpha over 2 squared in both terms, don't I? I can factor it out and pull it out in front. So I've got z sub alpha over 2 in front, square root of y over n times 1 minus y over n for that first piece, plus z sub alpha over 2 squared over 4n squared. This is, again, just the numerator in there. So again, as n gets big, what happens to this term? That goes away, doesn't it? Right? And then we've got p times 1 minus p over n times our z sub alpha over 2. And then again in our denominator up here, this is going away and we just have a 1. So as n gets large, this part here looks like the original confidence interval that we had. So again, this second form of the confidence interval is different from the first, but as n gets large, they become closer and closer. The whole reason why we have this second approach, of course, is that if we've got smaller sample sizes, we might need a little bit wider confidence interval, which just helps us get. So it was the only real reason why I wanted to go through that particular one, is because it gives us a couple of different notions for confidence intervals. So just to write both of them down again, the first confidence interval looks like y over n minus z sub alpha over 2 square root of p times 1 minus p over n, and then the same thing on the right. That's the first one. And this is the one that you're going to use the most often. Because again, most of the things that you're going to deal with, especially if you're really trying to get a confidence interval for a proportion, you're going to use a large sample. If you're thinking about population idea. If you're looking at health insurance and want to try to get an estimate for what percent of the population has a certain genetic disorder or disease or what have you, you're not going to sample 10 people. Right? You're going to do a large sample size. Right. But another one, of course, is the one we just came up with. It's that y over n plus, let me rewrite, make sure I rewrite the way I had it before, z sub alpha over 2 squared over 2n, that's a 2, over 1 plus z sub alpha over 2 squared over n, and then minus z sub alpha over 2 square root of y over n, 1 minus y over n, z sub alpha over 2 squared over 4n squared over that same denominator. I'm not rewriting that whole thing. I'm not rewriting it. It's not going to happen. I mean, it's literally the exact same expression, except you take out the minus sign in the middle and put in a plus.
So how do we tell that, okay, we can't use the simpler version?
So the simpler version, if your n's like 5,000, you're going to be using it anyway, because obviously your z sub alpha over 2 is not any better, bigger, or anything like 2.6 if you're using a 99% confidence interval. But in general, it's the same kind of idea of when we're able to use a normal approximation. If your n times p and your n times 1 minus p are both bigger than 5,
Yeah.
it's probably a good estimate that you can just go ahead and use the simpler one. Same rule of thumb. Not perfect, but
Yeah.
I mean, if you're computing it on a computer and have that thing programmed in there anyway, you can spit out both of them and see how close together they are.
Yes.
Yeah. So I mean, in general, you can spit if you're going to put this in something like Excel, which is going to have this stuff built into it anyway, it's going to use the first one and not the second. So if you really want to check, you program the second one in and see what happens, because it's going to spit out the first one anyway. All right. There's a third one as well. Did that make you happy? The third one's a little bit easier to do instead. So instead of going through this craziness with the confidence interval, if your probability of either success or failure is really, really low, so say your probability of success is low. I mean, like 0.1% of the time something happens, really, really low. It's conceivable that you could take even a large sample of 1,000 and not get any successes. In which case, you're going to get 0 for your confidence interval. Right? Because your p times 1 minus p over n is going to be 0. Because the estimate you're using for your p is y over n. Okay? So in those cases where probability of success is really, really low or really, really high, in the really, really high case, again, you might not have any failures. So your 1 minus p would be 0. Okay? In those cases, you might use a slightly different estimate for your population proportion, which your book is using for a p tilde. You're going to use number of successes plus 2 over total number of trials plus 4. All right? And then use your normal confidence interval.
This is random.
It does look random, doesn't it? It's not really, though. So let's go over here to this piece right here. It looks really random, but it's not. Okay? So if we look at this piece here, this one... the heck did that go? It really flew, didn't it? Hello. Oh, it's stuck. That was fun. All right. Looking at this piece here, this is our p hat, right? If you're doing a 95% confidence interval, what value do you use for z sub alpha over 2? That's for your alpha over 2. So what do you use for z sub alpha over 2? What's the z-score at that? 2.4. Too high. It's 1 point. That would be at 10% instead of 5. You're close. It's somewhere in between. It's the 1.96 one. Yeah. 1.96 is about what integer? 2. I square 2, I get 4, right? What does this simplify to here? Yeah, that simplifies to a 2, doesn't it? Right? And then the same thing here, that'll be a 4, won't it? Okay? So notice in that case, if I multiply top and bottom by n, I get that. So it looks random, but it's not. It's saying, okay, well, what if I just treat the z sub alpha over 2 as 2 and simplify things? That's what we get. Okay. So it looks random, but it's just based on what that is to try to get an approximation. But notice if you use this approximation, even if you get no successes, you still get a p-value that's not 0. Right? So if you get no successes in a really, really high number of trials, you get a non-zero p, so you get a non-zero confidence interval. That's the whole point. So even though it looked random, it really wasn't. And it's just trying to help us get a non-zero idea for the confidence interval. We'll be able to go through it that way. Does that make sense? The problems, obviously, hopefully it's obvious, are literally just plugging in numbers into these things. I mean, it's just a matter of getting the confidence interval. So instead of doing an example in the last 3 minutes of showing, hey, by the way, you should know how to plug numbers into a formula, I think I'll just stop. Sound fair enough? Okay. All right. Have a good one. See you later.
So for exam, from what section did we start over?
Started in 5 point. 5. Because we went back and did. Well, we also did. Talk about moment generating function stuff too. Because we went back and proved the central limit theorem. So we went back earlier in chapter 5 and did some of that stuff. Even though we had done it last semester, we went back and talked about moment generating functions and talked about limits of moment generating functions so we could prove the central limit theorem. And we did some more central limit theorem problems. So did central limit theorem problems and then up through 6.5. All right. Oh, that was weird.